RC22. I welcome all the participants once again. I have shared the flyer and you have noticed that this is a 3-day program in which we have 4 lectures. Among those 4, we have 3 lectures on quantum grades, Heisenberg, Sommerfeld, and Dirac. And we also have a lecture by Professor Ajoy sir on the last day. And we have 2 very anticipated interviews. One is with Professor Ghatak sir. He's already online with us. Everybody is keen to hear to Professor Ghatak sir. That is on the second session from 7:30 to 8:30. But the first session, very young and dynamic Dr. Mrittunjoy will talk on Heisenberg, who has thrown away the Bohr's orbits. Welcome, sir. Mrittunjoy Guha, sir.
Thank you.
Then this is also the occasion of 50 years of the book of quantum theory and quantum mechanics theory and applications by Ajoy Ghatak, sir. From 7:30 to 8:30 p.m., Professor Ajoy sir will be interviewing him. This is the schedule of the 3-day program and today's program. With these few words, I welcome all once again. And I hand over proceedings to Professor Ajoy sir for a few inaugural remarks. Professor Ajoy sir, please.
Thank you very much. I'm very happy that we are having now this third set of lectures on celebration of International Year of Quantum Science and Technology. And this program we have planned for whole of the year. This is basically a program which will offer us glimpses of the history of the quantum mechanics and the landmarks which happened as a result of the last 100 years of hectic work in this field which has changed the world in which we are living today. And we are very happy that we have today one of the most respected and known professor of quantum mechanics with us, Professor A.K. Ghatak, and also a very young physicist and also a quantum scientist, Dr. Mrittunjoy Guha Majumdar. And we also have very distinguished participants here in today's session. We have also Professor P.C. Deshmukh here, and we are going to have a session with him also tomorrow. I think this is a great opportunity to listen to the latest and one which is within us and which we have really imbibed from the best of the books available on the Indian scene, I would say, though they are international books. But I think these books are also a kind of a landmark books on the horizon of physics education in the country. And we are celebrating these 2 books, one by Professor Ghatak, which is completing actually 50 years of its presence in India and internationally. Sir, I bought your first edition actually of the book in 75 itself. And its title was Quantum Mechanics. And I can see that it has evolved over the years. And now you have even changed the name of the book slightly with some add-on to it, which is very interesting.
Thank you.
Also, when we actually planned that we should have Professor Deshmukh also in this particular program, the idea was this, that his book is a very latest book.
Yes.
And we thought that why not bring both our respected members of IAPT also together here in this particular program and listen to their experiences of creating such resources which are, life-changing for the students. If you allow me to put it like that, I think part of it is there with us now. As Professor Y.C. Sharma was also saying, if anybody asks me, okay, which is the best book, I can immediately tell him, go buy that. It's a very interesting book. And I think after coming of Professor Ghatak's book, people stopped buying Shiv's book in India. So that is also a fact. And because I met Dr. Mrittunjoy in Dharamshala, that was a very interesting meeting. We had a session on the latest in quantum, particularly on quantum computing. So Professor Deshmukh and Professor Mrittunjoy both were in that particular session in which we had their lectures. So I thought that maybe the wider audience of IAPT should listen to young people also. Very exciting. Every day new news is coming about quantum computing. Today itself, I was seeing that there is one 56 qubit machine which has done something very interesting. And then over a distance of 30,000 kilometers, a message has been passed without breaking. I think these are grand news which are coming on the horizon of physics itself. So I welcome you, sir. Welcome both our today's speakers, Professor Deshmukh, our very respected IAPT fraternity members, students, and I'm sure students will definitely enjoy listening to the giants of Indian physics. So thank you, Professor Madhusudan, back to you.
Yes, thank you very much, sir, for your initial remarks. Now I request Professor V. Rajeshwar sir, Vice President IAPT South India region. He is from RC22. I request Professor Rajeshwar sir to speak few words.
Professor Good evening, everyone. Good evening, everyone.
Yes, sir. Audible. Please go ahead.
Honorable President, Dr. Rahul Walia, sir. Dr. Ajoy Ghatak, sir. Dr. Deshmukh, sir. Dr. Mrittunjoy Guha, sir. And Dr. Madhusudan and all other members of IAPT. I think that this is a great initiation taken by IAPT National Committee. And this is the third time that we are conducting an online program at the national level. Previously, we have conducted on quantum mechanics and quantum computation. And the two programs were very much successful. And now on this special occasion, we got a chance to present ourselves. I hope I think the interaction with either Ghatak sir and other eminent people will definitely help us. And quite recently also, we have discussed among ourselves, IAPT RC22, that we should reach all, say, schools. Quite recently, we have discussed, myself, Madhusudan, that we should plan for, say, to propagate all of these things at the school level. So that we are going to start very soon. So, and I thank each and everyone who are taking a part. And I also thank, I think Dr. Somashekara sir is also available in this gathering. Welcome, sir. And on behalf of RC22, a warm welcome to all of you for a healthy discussion during these 2 hours. Thank you.
Thank you, sir. Now, without wasting time, let me ask Dr. P. Sangeeta Lakshmi ma'am, who is the senior member from IAPT RC22. Madam, are you there?
Yes, sir.
Now I request Dr. P. Sangeeta Lakshmi to read the profile of Dr. Mrittunjoy Guha, who is the first speaker of today's program. Madam, please go ahead.
Yes, sir. Good evening, one and all. I am Dr. Sangeeta Lakshmi from St. Pius 10 Degree and PG College for Women, Hyderabad. It's my great honor to introduce Dr. Mrittunjoy Guha Majumdar, is Sir, and he is a renowned professor at the National Institute of Advanced Studies, Bangalore, and assistant professor at Amrita Vishwavidyapeetham, Delhi, NCR. Having completed his doctorate from Cavendish Laboratory at University of Cambridge, he has been an institutional postdoctoral fellow at Harvard University. He is a senior postdoctoral researcher at the Indian Institute of Science, Bangalore, funded by the Office of the Principal Scientific Advisor to the Government of India. He is a postdoctoral associate of Nobel laureate 1973, Professor Brian Josephson at University of Cambridge. He has been a Trinity Barlow Scholar from 2015 to 2018, a Nehru Scholar from 14 to 18, Inspire Scholar from 2011 to 14, and TIFR NIS Fellow from 2012 to 2014. He was a lead speaker in the domain of quantum error correction at the National Quantum Mission NQM Strategic Consultation Meeting in July 2023. His area of research expertise is in entanglement, quantum information, and the foundation of quantum physics. Has had training in artificial intelligence from MIT Schwarzman School of Computing, with one of his recent research focus areas being quantum machine learning, QML. Dr. Guha Mazumdar has previously worked with Ministry of Human Resource Development, Government of India, UNESCO, and G20 on education and science policy. He has also been a science communicator with his documentary on quantum mechanics aired on Doordarshan under the Science India initiative. Sir, we welcome you all with great applause, and please continue your session, sir. Thank you.
Dr. Mrittunjoy sir, go ahead.
Okay. Thank you, Dr. Sangeeta ji, for that very kind introduction. Firstly, I would like to pay my respects to the very eminent members who are out here today. I have, as many of us have grown up reading and studying the works of Dr. Ajoy Ghatak. I've had the privilege of interacting with him in the past, and he's as kind and humble as he is eminent in the area of physics, which doesn't need any introduction as such. Professor Deshmukh, of course, we have been in touch recently, but we haven't been able to connect on some areas of research focus. I hope to kind of interact with him shortly about that. Dr. Ahluwalia, who has been very kind and I've been in touch with recently as well, and the various others I look forward to interacting with. So today's talk that I will be delivering is primarily on a foundational aspect of quantum mechanics. I otherwise work in the area of quantum information and entanglement theory, which comes a little later in the historical trajectory of quantum mechanics than the period that I am looking at. Having said that, there has been some work on the area of wave-particle duality and its connection to entanglement concurrence that I have in the past worked on with Professor Dipankar Home at the Bohr Institute in Kolkata. So today's talk, without further ado, I will share the slides so that I can begin with the discussions. Right, so I have named it The Uncertain Breakaway from Bohr Bits. The reason for doing that is, of course, as the word suggests, I mean, Bohr bits is, of course, Bohr orbits, but it also has a German meaning to it, which is to do with the drilling aspect of things, and to look at how certain deterministic drillings can be done into the nature of reality as such, which I believe was moved away from when it came to the developments with Heisenberg, with Max Born, and various other contemporaries during the the mid and the late 1920s, particularly. And so that is an important aspect that we will be covering today in today's lecture, so to say. So when we talk about Bohr orbits, I think we have to go a little back in time, essentially. There was the very eminent physicist by the name of Haas, right? But before I come to Haas, actually, so the idea of what is reality, right? What is the nature of reality, especially to do with fundamental particles, particularly electrons for that matter. And there was a lot of discussion on how the atoms are oriented, what are the ways in which the constituents of the atoms are oriented. And so it was seen that in the late 1800s, there was a lot of discussion on classical electrodynamics and whether that can have a connection with the way in which the orbits or the orientation of electrons in the atoms can be explained. So we all are familiar with the plum pudding model, which looked at how there was a kind of a central core of positive charges, let's say, and then there were these raisins, which were seen as the electrons of sorts. Rutherford's model, of course, went a little further in terms of explaining a positively charged nucleus, but didn't quite address the aspect of electron stability beyond a point. There were certain aspects of it which were not explained to the ultimate extent that it should have been. And could be done later on, because in physics we see that there are a lot of different interpolations and informed kind of choices one takes with respect to the conceptual frameworks, given the kinds of experiments that are happening as we go along. And so the idea of spectral lines essentially was very important, and that kind of led to the initial discussions around how to look at this aspect of quantization. Before I move forward to Haas himself, I would like to highlight that physics, of course, had seen a revolution, actually multiple revolutions, about 5 years before this, about 1905 with Einstein's four-pronged kind of revolution, which had special relativity, general relativity, Brownian motion, and the photoelectric effect in the year which is we know as Annus Mirabilis, or the year of miracles, 1905. In 1910, Arthur Eric Haas came forth with this idea of the hydrogen atom and the electron kind of circulating on the surface of the sphere of positive charge with a constraint on the motion itself, right? So he had constrained the potential energy of the electron itself to be equal to a certain kind of frequency that he spoke about, times, of course, the Planck constant. So he's often regarded as one of the first people to kind of have spoken about it in this respect. A very interesting tidbit that I got to know while kind of looking more deeply into these works was that Haas was actually, and please correct me if I'm wrong here, the last doctorate student of Ludwig Boltzmann, who himself in 1877 gave the first precursor, or the first statement of sorts, of the discreteness of energy levels, although not quite in the context in which later on Planck and Einstein and various others came forth with. And so he's often regarded as having made the pre-discovery of Bohr's orbits, so to say, although it was not quite in the way that Bohr came forth with it. Nicholson thereafter looked at quantizing, especially the angular momentum side of things. I'll be focusing a little more as I go along in one of the slides on Nicholson's work and how that informed Bohr's work going forward, and things that went on after that. Bohr's research, of course, laid the foundation of the atomic model. There are a few graphic slides or rather pictures that I've shown here. One is that of Haas himself, who worked in various seminal ways in this area. The Solvay Conference of 1911. We all know about the Solvay Conference of 1927, where we have this very famous photograph of the various physicists, very eminent physicists, the who's who of quantum mechanics, so to say. And from 1927 to 1935, we have the series of discussions that take place, the correspondences between Einstein and Bohr as such, the famous Bohr-Einstein correspondences. But it was in 1911 that there was a lot of discussion on radiation, on fundamental aspects which informed how Bohr took it forward, as well as later on how the other pioneers who formulated the new quantum theory, so to say. So we must appreciate that there was a certain kind of transition from the old quantum theory to the new quantum theory. And the work that I'm going to put forward is actually the starting point of sorts, one of the major works that brought forth the new quantum theory in 1925 and just after. Now, Heisenberg, I'll come to Heisenberg in greater detail later on. But I've always believed, especially when I was at Cambridge, there's a way in which some of my guides and mentors, sometimes things happen in very nonlinear ways when you talk about formulation of physics or understanding of nature itself. And Heisenberg was particularly kind of a little, they say, I mean, he was perturbed. He was having hay fever as well, apparently, as per the story goes, because he was, he was perturbed because he was looking at the spectral line phenomena, and then he was trying to explain that. And there were certain kinds of discrepancies, there were certain anomalies that came forth. And it said that he went to this place called Heligoland, which is in the North Sea. And that's where you basically had the first formulation of the non-commutative observables aspect of things, which he postulated, or he posited just after coming back from his holiday to this beautiful little island in the middle of the North Sea, which is called Heligoland, essentially, right? So just to give a little bit of context before we go into further details on this front. So Nicholson, I mean, gave this idea of, this idea of the proto-elements, essentially. He was very interested in a couple of ways on resonances or even direct applications in astronomical data. And this is very interesting because here we are talking about atoms, we're talking about electrons, but he posited this idea of the proto-elements, and particularly 4 of them, which is not quite the elements as they are on the Earth, or let's say as we find around us, but something which he spoke about in terms of, for instance, on the sun and beyond in astronomical data as well. And he was one of the first people who formulated this idea that the frequency aspect of how the electrons are oriented within the atom, and the vibration, so to say, right, of the electrons in the atoms themselves, was put forward. I mean, so there's an illustration that I've taken from the cited paper that you have at the bottom, and he kind of put forth this idea in the very beginning. However, we have to be very careful in terms of understanding what the frequency here means and what Bohr had mentioned in his 1913 model, which is not quite the same. So the spectral frequencies and the actual vibratory frequencies, I mean, as has been put forward by Nicholson, don't quite match, essentially. I mean, they're not quite the same, because here we're talking about actual vibrations in the way that has been illustrated in a very kind of rudimentary way. Whereas Bohr, of course, was talking about transitions. He was talking about the energetics of the system itself. And so it would be naive to kind of draw parallels in that way, although we do say that Nicholson had a certain form of proto-discovery as well of some aspects of the Bohr model, so to say. So in 1913, we come forward with this very well-known paper. This is the original paper itself. I have put this, this snapshot of sorts, the Philosophical Magazine and Journal of Science, published in 1913. And of course, we're all familiar with the various aspects of it, where he spoke about, I've written 3, but actually I've ended up mentioning 4. I mean, they're all connected in certain ways. So electrons, of course, revolve in stable, discrete orbits without radiating energy, which is called as stationary orbits. There are certain kinds of angular momentum quantizations. They come in discrete packets, essentially, the angular momentum itself, in terms of integer multiples of that. The smallest orbit, of course, is given with respect to the Bohr radius, which is defined for hydrogen as 0.0529 nanometers. And of course, the energy levels, right, the way in which electrons can absorb or emit energy by jumping between the levels, given by the Planck's relation, and the emitted or absorbed energy, essentially, which is given in that manner. Now, unlike Einstein, Bohr didn't quite accept photons in the very beginning. There are some correspondences and discussions which kind of look into this aspect, but relied more on the Maxwellian kind of formulation of electromagnetic theory itself, and looking at the classical radiation frequency with the electron orbital motion in large n states. There is a BKS theory I'll be coming to as well. It's a theory which is called the last old quantum theory attempt at trying to understand various aspects of the physics of these atomic systems, which didn't quite hold its ground, and it was replaced by the Heisenberg and the Schrodinger's wave equation aspect of quantum mechanics, so to say. So BKS is obviously looked at as a seminal work within the old quantum mechanics formalism, and in fact, the last one at that, essentially. So there are a few things that, I mean, as we say in physics, of course, it's all about, various kinds of observations and the divergences, so to say. And Frank Hertz in 1914 came forth with this very well-known experiment of electron colliding with a mercury atom. And there are very specific kinds of kinetic energies, right, where which is seen to be kind of emitted of, or rather absorbed of sorts, right? And so this confirm the Bohr model, so to say, right? Because there are certain discrete energy level characterizations that were kind of looked at. It was not looking at various other aspects, which we will look at as we go forward in terms of the experiments themselves. And so the idea that there are continuous energy variations of this classical expectation of sorts is not holding true, would not hold true. And that was somewhat explained by, Bohr's atomic model, so to say. So this was just after, 1 year after Bohr's, the first paper, the seminal paper. It was not his first paper necessarily. As far as I know, that's the 1913 paper, and thereafter the Frank-Hertz experiment. Now, there are some fundamental problems that were seen with the Bohr-Orbit modeling, so to say, which is one, of course, is that there was preeminence or importance given to hydrogen or hydrogen-like atoms, right? So helium and the Li2 plus should have the plus in the superscript. That's a typo there. But it fails for multi-electron atoms due to certain kinds of interactions, right? And we are all familiar with the shielding effects, where because of the electron cloud in the inner orbits and orbitals in a later context, there is a certain shielding that happens for electrons that are more outside in the outer shells, let's say, and that obviously has various non-trivial effects on the physics of the system. Thereafter, the fine structure, the additional splitting of these spectral lines due to various kinds of aspects. I mean, you obviously have the spin-orbit coupling, you have relativistic corrections, that is not quite accounted for by Bohr's model as such. And then there are aspects of electron spin and intrinsic angular momentum, which was not sufficiently backed up by various other aspects that came forth over time. Then we talk about molecular structure, the aspects of covalent bonding, for instance, and even the periodic table. There are many aspects of the molecular orbital theory, the valence band theory, for instance. All of that was not quite there when we talk about the Bohr's discrete orbit model, which did come across in different kinds of experiments and studies thereof. And of course, the aspect of accelerating charges, right? And the idea that when orbiting electrons were to radiate radiation, then, what about the stability of the atoms, so to say? And finally, of course, the Z-man effect, which I'll be speaking about as well a little bit, leading to the spectral line splitting in magnetic fields that remained unexplained with this kind of an idea. One aspect here, though, is that the Z-man effect was there from 1896, but the explanations thereof were done over the next 2 or 3 decades, one would say, right? So 1896 is when I think it was first kind of observed in certain experiments, but of course the explanations were given a little later. So the idea of the fine structure kind of aspect of the spectrum, so to say, of course, the classical aspect would be to look at a ground state and the V Coulomb, so to say. But then we can have relativistic corrections. One can have spin orbit corrections, and thereafter, of course, the Z-man corrections, which makes it much more finer. So it is almost like the evolution or the trajectory, so to say, of how the spectral line analysis was done and the physics thereof, which explained the various aspects or nuances of this, essentially, right? So that is very, very important to understand, because this evolution, this way of kind of explaining was, fundamental, was seminal, was foundational in terms of formulating the theories that we did over those first few decades of the 20th century, so to say. So then we come across a little further to the Stern-Gerlach experiment, where certain nuances of the Bohr model or the Bohr atom kind of was further kind of questioned. The Stern-Gerlach experiment, of course, is a very well-known experiment that looked at the quantization of the angular momentum of the electron spin, and this obviously was not quite in line, because there was not much of a description, so to say, of orbital angular momentum. And the way in which the splitting happened and why it happened, I mean, I've given the experimental setup out here, and things, for instance, like spin-based formulations or even the Pauli exclusion principle were not, quite there at the time. So the Stern-Gerlach, again, raised a few questions with regards to the orbit model that had been prevalent, before 1925. So this was 1922. And then, we move a little further in 1925 to 1927, when, the new quantum theory kind of finds its footing and goes forth from there. So, and then, of course, the Z-man effect. I just wanted to highlight the Z-man effect, 1896. In this case, you can see that there are different kinds of, single line spectral, characteristics. which one can see for certain kinds of mercury vapor lamps, for instance, that splits up into multiple components under magnetic fields. And then you also have the other, the longitudinal Zeeman effect as well. In case of, so there's a transfers and the longitudinal Zeeman effect, so to say, right? So this is observed in the laboratory, but this was not quite, again, able to be explained in terms of the Bohr model and align more with the further theoretical exploration that happened after. And then, of course, you have the very well-known Davison-Germer experiment in 1927. Do note that this was after you had the new model of quantum mechanics already having been formulated. In fact, even the Schrödinger's side of things with the wave mechanics was in the picture. But I just wanted to highlight that the way in which this was looked at in terms of the interference patterns obviously looked at it in terms of not having the wave part. I mean, Bohr didn't think of the wave particle duality as such at all, whereas Heisenberg came forth with the uncertainty principle and the various other associated concepts. So the Davison-Germer experiment, of course, does not quite align with the Bohr's orbit model, which looked at electrons as particles in certain orbits and did not quite address the wave particle nature of things. So, of course, this is a very important experiment that helped in terms of formulating quantum physics as we know it today. So now, I mean, there is a question which people ask about the nature of reality, and even within quantum mechanics, there are the two primary schools of thought. So we often talk about the wave function, for instance, but the wave function itself has two schools of thought or interpretations, which many of us will be familiar with, which is that of the psi-epistemic and psi-ontic schools of thought. So when we talk about the psi-ontic schools of thought, we talk about when we are considering the wave functions to have an ontological or an ontic aspect to it, but it is actually a physical kind of reality, so to say. It's an element of the physical reality. So Bohmian mechanics, of course, is talked about in terms of the pilot wave theory and so on and so forth. Whereas the psi-epistemic is when you're talking about the epistemological or how it describes reality rather than being reality itself. And of course, it leads to realistic elements like the probabilities of finding particles or quantum systems in certain states. But by itself, whether it is a part of reality or it is real in the sense of the ontological side of things has been a matter of discussion. So now in 1925, there was a lot of anomalous aspects with the spectral lines, with various other experiments as well. And physics was stuck between these classical intuitions or semi-classical approximations, because even the old quantum theory was semi-classical to a large extent. I mean, there were a lot of aspects of semi-classicality which was there. And that didn't quite kind of, fall in line with these very strange experimental results, so to say. So Heisenberg, so there is another context I always kind of put forth, that is, in physics, there is often this leap of sorts, a conceptual leap that one takes, and that makes all the difference. So for instance, when Einstein took the leap with talking about the photons as the packets, there is a fundamental leap from when Max Planck talked about the discretization, or rather the quantization, in terms of the resonators that give rise to the quantum packets, right? The packets of energy. And the basis for the jump that was taken by Einstein was very much present, but that fundamental leap did make a lot of difference, essentially, right? Similarly, Heisenberg, when he spoke about this aspect of the observable quantities over the visualizable models, right? So there is a very fundamental, I mean, I wouldn't want to talk about metaphysics or foundations in that respect, but the way, the vision, the way of looking at the systems themselves, right, there was this fundamental shift, so to say, right? So the idea was no longer about what is, but it was more about what is observed, essentially, right? And only keeping to that primarily, right? Not kind of trying to find a more classical or semi-classical approximation of, visualizing it in terms of specific trajectories, for instance, and so on and so forth. And that fundamental shift, right, which happened in 1925, was what was very important in bringing forth the new quantum theory, right? And there was a lot of discussions with Max Born later on, and also Niels Bohr, interestingly. In fact, Niels Bohr, gave him a job as well, I think, Heisenberg at one point, to start working with him. And there is a whole episode of what happened during that time. They did develop a lot of things in terms of complementarity, and in terms of uncertainty principles on the two sides of that discussion. So the Bohr-Kramers model, I don't want to kind of go into too much detail on that. It was basically trying to look at a few things in terms of there are fundamental premises which are very important here. So the first line I've already mentioned, there is a classic wave description given in the old quantum theory side of things. And they didn't want to quite align with Einstein's photonic aspect of things as well. One aspect there that they mentioned in third line, if you see the third point I have mentioned out here, I should have highlighted that energy and momentum were proposed to be conserved only statistically, right? Not in the individual interactions. So there was an aspect of large systems and statistical ensembles or averages kind of having this energy and momentum conservation, but not quite in terms of the individual aspect of things. So the electromagnetic wave field was still treated as a continuous classical wave, and the photon aspect was not at all in the picture, so to say, right? And John C. Slater, for instance, because BKS has Slater as one of the people in the triad, right? He did mention that the photons exist, but they exist in terms of being guided by the classical wave fields themselves, right? So Bohr and Kramer didn't go by that idea, but they modified it to discontinuous quantum transitions, right? They didn't, and still did not look at the conservation aspect of things beyond a point, right? So this was further developed by Heisenberg, Bohr, and Kramer, but there were two experiments which were very important during this period. So the BKS theory came in 1924, the Bohr-Geiger theory, which was to do with coincidence detections, and the Compton-Simon experiment with Compton scattering and so on and so forth, did look at the conservation aspect more specifically and did see that the energy momentum conservation has to be kind of maintained of sorts, disproving the statistical conservation hypothesis theory of BKS, right? And so Wolfgang Pauli was a very strong critic, and there is this term I've used here. He called this theory the Copenhagen putsch, right? Which is basically that it is a theory that should not have, come to be. And I don't know the etymology of putsch per se, but it's clearly something which is not quite flattering in its own way or very positive as such, right? And in fact, Max von Laue also said that the BKS failure saved physics from being misled, right? So there were very strong views that came forth about the BKS theory after the 1925 experiments and the experiments thereafter. So if we move forward, so Heisenberg's realization, right? There were certain realizations that came to be. I mean, one was, of course, the experimentally observable quantities, right? The transition frequencies and intensities, how they can be formulated. He said, well, electron orbits as conceptualized were seen in experiments per se. They were never directly observed, so to say. What is observed are these absorption and emission spectra, right? These are what are observed in experiments. There is not one experiment that talks about actually the movement of the electrons in the orbits or otherwise, right? So he, introduced this aspect of transitions. And I will later on mention a little about how the matrix mechanics came to be from these transition-based calculations or considerations. And that naturally led to this consideration of arrays, right? Arrays of different numbers, essentially, which related to the transitions in specific kinds of systems. And these arrays, after that, Max Born took them further towards the matrix mechanics aspect, the mathematical formulations, and how that was utilized thereafter. And so position and momentum, for instance, till that time were looked at as classical variables. But after that, of course, as we know very well, there was this aspect of putting them in terms of matrices. And most importantly out here is this conceptual element of non-commutativity, right? This aspect that if you were to have a sequentiality for how you operate with different kinds of operations or experimental kind of tests, let's say, right? I mean, one of, let's say, looking at the position and then the momentum, or the other way around. In classical mechanics, of course, we do not have this ordering mattering all that much, right? So you can have the position and then the momentum, or vice versa. But of course, within quantum mechanics, there was this first element of the non-commutativity, which said that the ordering did matter, right? That there was a very non-trivial aspect of that ordering, essentially. Of course, also the quantum states themselves, how they moved forward evolved in terms of the operators themselves, was in terms of the matrix equations that came to be from this very logical way in which they went about with it, right? And I'll give further expansion on that as well. The uncertainty principle was also a direct consequence of this formulation, right? There was an aspect of different kinds of variables such as position, momentum, energy, time, various other complementary variables as well that had a certain inherent uncertainty of simultaneous determination, right? This is very important because even if I were to have, let's say, the best experimental apparatus out there, there is still a certain constraint that is fundamental to the very way in which quantum mechanics is oriented. This itself was formulated in terms of a thought experiment, which Heisenberg had formulated, which I will also briefly touch upon, which is his this microscope experiment, the gamma microscope experiment, where he looked at the perturbation in terms of the positioning and the momentum that is imparted to an electron because of observation, so to say. And so thereafter, of course, Bohr and Jordan kind of formalized these ideas into the matrix mechanics as we know it. So this is the experiment that we often kind of hear about, which is the Heisenberg's gamma ray microscope thought experiment. So in terms of the precision with which, let's say, an electron is detected, in a certain, region, let's say delta X, has a correlation with the power of the microscope itself. So if there is a deflection of this, the radiation itself, the sine theta can be given in terms of the lambda and the delta X. This comes from foundational aspects of how we look at light itself, and the spread of light and the way it kind of deflects off a certain center here, which is the electron itself. And thereafter also we can talk about the momentum that is generated as in terms of the light hitting that electron and what happens thereafter. So that delta px itself can be written in terms of the sine thetas and the 2h by lambda aspect of things. Because here we are basically looking at the x component. I have not defined the coordinates here, the basis, the axes, but there is a conservation of the momentum aspect of things. So the delta px can be defined with respect to that. And of course, if you take the multiple of the delta p and the delta x, you have a certain constraint, or you can say a value basically, which is coming out in terms of 4h pi. So this was actually the starting point of sorts. He tried to think about this very basic but very important kind of thought experiment, and that led him to further calculations and thereafter coming towards various ideas on the uncertainty principle front, so to say. And so thereafter in 1925, the uncertainty principle also, the work was going on after this as well. But in 1925, we have this very seminal paper. I got the English translation, but this is, of course, in German. And this paper was published in, please correct my German because I'm not at all familiar with it all that much, Zeitschrift für Physik in September of 1925. And the idea was that he was trying to look at, as I said, the transition probabilities rather than these unobservable concepts like the electron orbits. He was trying to look at initially, there is a small tidbit that I have mentioned in the sub point, in the second point, so to say, which is that he was trying to look at the hydrogen orbits as such, right? He was trying to look at the Fourier analysis, rather, very specifically speaking, of the classical hydrogen orbits. But however, the problem was extremely difficult. It was quite convoluted in its own way. So he actually went for the one-dimensional enharmonic oscillator premise, the kind of system, so to say, to kind of look at that a little more, and that is what gave rise to certain kinds of multiplication rules that came to be in the Fourier series itself, right? I will just mention about this when I talk about the wave mechanics side of things. And that aspect, the multiplication rule, so to say, for these kinds of Fourier series of specific quantities or specific variables in the system, was what gave rise to this understanding of the commutation or the non-commutativity aspect of things, right? So it's a very structured way, again, a very logical way in which he went about with it. He wanted to look at the spectral lines of the hydrogen atom, but of course that was not possible beyond a point. So the enharmonic oscillator, the Fourier series specifically of that, and then thereafter looking at the product rules, and that is what gave rise to the non-commutativity, right? So there is a very well-known paper, rather a comment by Weinberg, right? Steven Weinberg. I would like to kind of highlight this. So this paper by Heisenberg was often called as a very, well, for lack of a better word, this is not a very good word to use in physics or in the sciences, but it was pure magic, right? That's what actually Weinberg ended up telling you, right? In this particular, quote, for instance, he said that I have tried several times to read the paper that Heisenberg wrote on returning from Heligoland. And although I think I understand quantum mechanics, I've never understood Heisenberg's motivation for certain mathematical steps in this paper. Theoretical physicists in their most successful work tend to play one of the two roles. They are either sages or they are magicians. It is usually not difficult to understand the papers of sage physicists but the papers of magician physicists are often quite incomprehensible. In that sense, Heisenberg's 1925 paper was pure magic, right? So, I mean, there were a lot of aspects where even today, people are kind of, looking at different aspects of some of these mathematical expansions in certain segments. And Weinberg, being Weinberg, saying this is obviously something which is highly non-trivial and important to highlight here. So after that, in the immediate aftermath of this, Bohr and Jordan came forth with looking at this idea of infinite Hermitian matrices and taking the work forward in terms of the arrays, because the arrays of emission-based or spectral-based variables was what Heisenberg was looking at, but that was further extended by Bohr and Jordan in terms of infinite Hermitian matrices. And then Bohr, Heisenberg, and Jordan came forward with a three-man paper. This is a very well-known paper by the three of them, BHJ. And thereafter, Pauli was working on matrix mechanics as well, but he was looking more specifically in terms of the hydrogen atom. Do mind that this is all in 1925, right? So the three-man paper comes out so Bohr and Jordan go with this mathematical formulation in August, September. Three-man paper comes out in November. Pauli starts working in October. Lanchos, Bohr, and Wiener look at extending it to continuous motions in December, right? And Dirac, who was working at the University of Cambridge at that time, looked at the Q number formalism of looking at this thing in late 1925 as well, successfully handling these many electron kind of systems, so to say. And then the next year, Heisenberg and Jordan take it to the hydrogen fine structure and the anomalous Zeeman effect, which was one of the key reasons for rethinking about physics in many different ways. And this was in April of 1926, right? And then thereafter, Heisenberg also looked at the aspect of resonance, quantum mechanical resonance, in terms of the helium atom systems in July of 1926, right? So this is August 1925 to July 1926. There are literally 6 or 7 very, very important physics-based developments that happened in this period of time, right? And so Dirac, for instance, he spoke about the Q numbers. So I just gave a bit of this is from his own paper, actually. So he said, the new quantum mechanics looks at a scheme of equations that are very closely analogous to the equations of classical mechanics, but there are certain kinds of fundamental difference, particularly to do with the commutative law of multiplication. And if one were to suppose, one cannot suppose the dynamic variables to be ordinary numbers, but one can call them a special type of numbers, right? So the Q numbers comes from that aspect. And the Q numbers can be generally represented by matrices whose elements are the C numbers, essentially, right? The functions of a time parameter and so on and so forth, right? So Dirac gives this in one of his writings around that period, 1925-26. And he spoke about that as such, right? So that is his idea of the Q numbers, which came in December, I think, or rather, it came in late 1925. There's a few months that went into this as such. Now, in 1926, January, Schrödinger comes out with the wave mechanics part of things, right? Born looks at the Schrödinger's wave equation and gives us the famous Born rule, right? The measurement rule of sorts. And this is accepted by Bohr and Heisenberg. I'll briefly touch upon how there is an analog between the Heisenberg model and the Schrödinger's model. Then thereafter, Dirac and Jordan come out with the equivalence, which I was talking about, the wave mechanics and the matrix mechanics of Heisenberg and Schrödinger in December of 1926. And then please note that Heisenberg came out with the uncertainty principle in the March of 1927, right? So this is a good 2 years after his initial paper that came out, which spoke about the new quantum physics and especially the non-commutativity from the emission spectrum kind of side of things. And then complementarity principle comes out in late 1927. And then Bohr obviously looked at the Copenhagen interpretation. Do note that in this period, there was a little bit of difference of Bohr and Heisenberg, but then it came around to them actually working very closely together to the point that, complementarity and this aspect of uncertainty, the way this came about actually has a certain, I wouldn't say a common kind of ground, but they were working very closely as such. And these are two different directions in which they took their work, so to say. So matrix mechanics, as I was saying, Heisenberg was looking at the Fourier series representations of the position itself and trying to look at this amplitude of transitions that happen between different energy levels. But looking at the Fourier series of two quantities, let's say position and momentum, the transition amplitudes that I have mentioned about here did not combine in the usual commutative manner, so to say, right? So there was basically an element of arrays that got generated because of this kind of a multiplication. And this non-trivial generation of element of arrays could be translated into a tabular kind of structure, right? Which is what Max Born actually saw, and he said, well, this can actually be looked at in terms of matrices, right? In terms of just as arrays or just as tabulated data in that sense, right? So when Bohr looked at the transition rules more, rigorously, then he saw that position and momentum, of course, have the non-commutative aspect of things, and the mathematical kind of formulation of that was put forth by Born and Jordan, so to say. And so you have these algebraic rules that were put forward. Dirac, of course, later on, after wave mechanics has also come into being, looked at bracket notations. Von Neumann looked at quantum mechanics in a more generalized vector space, Hilbert space formalism. There was a brief mention that I want to give about annihilation and creation operators that also was looked at by Born, Heisenberg, and Jordan. And these basically helped us in terms of preserving certain kinds of Hermitian properties, right? Because Born and Jordan, if you remember, had looked at infinite Hermitian matrices to explain the array-like aspect of the data that came forward from this, formalism, so to say, right? And do note that Heisenberg had spoken about the enharmonic oscillator aspect. So he had also had various kinds of additional terms like x cubed and so on and so forth that also gave rise to non-trivial aspects in terms of the generated data and the formulation, theoretical formulation, so to say, right? So we have to be aware of that aspect also, right? Max Born, of course, played a very important role in all of this, right? I already mentioned that he was the one who actually looked at the arrays translating into actual matrices. And, they developed a lot of aspects of quantum mechanics. The density function aspect, the probability density function was what he got the Nobel Prize for in 1954. And that is what he's often remembered by. But what we often don't remember is that he worked very closely with Heisenberg on the matrix mechanics side of things. And that is very, very non-trivial and extremely important for physics as such. I always kind of, remember this tombstone, right? This epitaph of Max Born, where he actually did mention the non-commutative relation between two canonical kind of coordinates. And that is on his epitaph, so to say. So that's just a little bit of a tidbit, which I find very fascinating. So then thereafter, of course, complementarity comes in, which is a little later in 1927, where Bohr was talking about this aspect of non-commutativity beyond the position momentum side of things, but in terms of more generalized Hermitian operators, of which position and momentum are, of course, very important. The uncertainty principle obviously was supported by this understanding of the complementary aspect of things. And there one aspect which is very important, which was not there in classical mechanics, is of course that of interference, though it is there in optics per se. But here we are talking about something more non-trivial, right? We're talking about things like, for instance, the wave function collapse. We have various examples, various kind of exaggerated thought experiments like the Schrodinger's cat experiment and so on and so forth. And when we come to entanglement, which is what I usually, which is my area of research, we are talking about correlations that are not determined till the point of that measurement, to the point that it's not classical in nature, right? So classical correlations have, let's say, balls of different colors, and you send them apart. And of course, if you see the ball of one color, the ball of the other color will be elsewhere. But in this case, what we're talking about is till the point of the measurement, there is no determined kind of reality to those elements or those properties, essentially. And that kind of interference across, spatial, distances, and in various other ways, temporal as well. There are some kinds of temporal entanglement experiments also that have been done fairly recently, gives us a different kind of thinking about interference and superposition and so on and so forth. And so this was very important. And so you see Bohr actually kind of took this forward in terms of the commutators of complementary variables and spoke about that, going forward. And complementarity also obviously aligned with the Copenhagen interpretation, so to say. And there was no independent reality, so to say, before the measurement outcome. So the centrality, the primacy of measurements and what is it described, what is the description of what you're seeing is more important even than what it actually may be, right? Which is why there is a lot of different interpretation that still exists as to what wave functions are, what quantum mechanics is, and so on and so forth. So wave mechanics, I just mentioned here, just to kind of highlight that there is a bridge of sorts between the two sides. Schrodinger's equation, of course, looks at the Schrodinger's temporal evolution with respect to the Hamiltonian. The Heisenberg picture instead looks at not the states evolving, but rather the operators evolving in time. And there is a one-to-one kind of way in which one can look at it. in terms of the commutators of operators and the Hamiltonians, the third equation that I've shown out here. And that the expectation value of this expression that you see leads us to what we know as the Ehrenfurst theorem, which is basically how we look at averages and the classicality, the average analogs, when we're talking about quantum mechanical systems, so to say. And so there is a theorem called the Stone-von Neumann theorem, where there is a unitary equivalence which is established between the Heisenberg and the Schrödinger's picture. And in various ways, we have Heisenberg picture actually being more natural for relativistic kind of considerations at times. And because while you have the state vectors that you do not kind of look at beyond a point, right? So you do not single out specific kinds of time or spatial coordinates or the frame dependence thereof. And therefore, the Heisenberg picture is sometimes better in terms of looking at such corrections and moving forward. So, well, I mean, why Heisenberg was right? We all know why Heisenberg was right, but I mean, there is a whole lot of experiments that happened after. The Davison-Germer I've already mentioned. Stern-Gerlach came before Heisenberg put forward both the ideas, the 1925 formulation and 1927 formulation. The double-slit experiment with the electrons, which recently was done by Hitachi, with 1,60,000 electrons being fired. And they obviously got the beautiful interference pattern that you see, which does look at the wave-particle duality of the electron itself. Then the Heisenberg's gamma ray microscope experiment that looked at the uncertainty principle. Thereafter, the Moss-Bohr effect in 1958, when the recoil-free gamma ray spectroscopy was looked at, again, looking at a different kind of uncertainty there, which is to do with energy and time, not quite position and momentum. And then, of course, my area of research in quantum entanglement, the non-commutativity aspect does have a role to play, especially when you talk about specific forms of even quantum information for that matter, where topology also plays a role and so on and so forth. We have taken it a little further from where we were, let's say, with 1982, when Alan Aspect first had those experiments on quantum entanglement. And now we talk about superconducting Majorana modes and so on and so forth, where the exchange or the braiding operations has a non-trivial role in terms of the operations of the gates that you can realize in terms of the quantum information side of things. Weak measurement, of course, also looks at how there are certain kinds of, a priori and post, post kind of measurements of sorts, and how you look at reconstructing what the system could have been in terms of the statistics of different properties of the system. And that also has refined this Heisenberg framework in certain ways in terms of the uncertainties inherent thereof, essentially. So Heisenberg has played a very, very important role, and that has been the theme that I was asked to speak about. And so I would like to highlight that even with quantum information now, and various foundational questions being addressed, I think Heisenberg is as relevant, if not more, as he was back in the day as such. So the lasting impact, of course, if I were to just summarize this, introducing the matrix mechanics, the formulation of quantum mechanics itself, there is very important this operator formalism that I mentioned in the third line, which is central to Dirac's work as well, right? Which became central to his work. So this whole idea of looking at the operators that may arise in different kinds of experiments or calculations in the quantum side of things. Quantum field theory, of course, when you talk about quantum mechanics and relativity, right? And that's where I mentioned about how the Heisenberg picture is well suited for that kind of, discussion, so to say. Of course, when we take it forward, Feynman, Schringer, and Tomonaga, seminal works by, them on the quantum field theory side of things. Nuclear physics, of course, when we talk about strong interactions and different aspects on that front, but not quite, there's no one-to-one kind of connection of sorts, but it's more foundational, which went forward in a very specific, sequence of steps, so to say, in the developments in physics, moving in that direction. Quantum information theory, of course, I already mentioned about quantum computation and cryptography. And the most important part is the idea of abstract mathematical structures being more important than intuitive classical visualizations, which no longer hold sway, right? They don't matter beyond a point. So again, the ontological to the epistemological transition that happened with Heisenberg's side of things, right? So in conclusion, I would say that Heisenberg, of course, when we talk about specifically the topic, the theme that I was, given as such, was to do with Bohr's orbits being replaced by Heisenberg. So of course, you have this very specific way in which it was done, and the observable quantities being primary. Classical determinism, of course, goes out of the window. And the last point that I've mentioned, the shift from ontology to epistemology, being a central theme in quantum mechanics, so to say. And so Heisenberg, has this very famous quote: "The problem of language here are really serious. We wish to speak in some way about the structure of the atoms, but we cannot speak about it," right? So the articulation that we want to do, right, may not quite be sufficient or proper to kind of actually understand the various aspects of what we are seeing in experiments. And what we actually need to kind of do is to rely on only the observables and formulate our quantum mechanics with respect to that. So with this, I would like to close my talk for today, and I look forward to discussions going forward. Thank you.
Thank you, Dr. Majumdar, for your well-organized and informative session. It was a wonderful presentation. You have covered all the topics, key points related to the evolution of quantum mechanics, with main focus being on Heisenberg picture. Thank you, sir. Now I request Dr. Professor Ahlwali, sir, for your remarks, and the participants can interact with Majumdar, sir, after the review of Ahlwali, sir. Ahlwali, sir, please.
No, thank you very much, Mrittunjoy. I must say it was a wonderful sweep which you presented about how Heisenberg came on the scene. I think the preliminary discussion which we had together on that Heisenberg was the man who threw away the orbits of Bohr, that very nicely came out of your presentation. I would say that your presentation was, if you allow me to say that, was not very easy to comprehend in a way, because it was a lot philosophical than normally we people encounter when we study quantum mechanics. Right. Thank you for giving us that kind of a viewpoint. And I hope that the participants here must be having a lot more questions which they would like to ask. But I must say it was a wonderful presentation. I think
I agree.
It was a great thing which has happened today.
Thank you. Thank you so much.
Thank you for the participants. You please can raise your hand and ask questions. Please don't hesitate to ask questions, because that is the essence of these kinds of discussion.
Dear participants, now it is open for questions. You can ask your questions. Guha Majumdar sir is ready to answer your queries.
Hello.
Yes, please. Yes, you're audible.
Sir, my name is Ritika Rao, and my request is to will you please elaborate more on the statement that Heisenberg dared to prioritize observable quantities over visualizing models. There was an example, but I request is to please elaborate more on that.
Right. Thank you for that. A wonderful question. I think that is central to what we discuss in quantum mechanics. So the whole idea of determinism, for instance, the whole idea of classicality as we know it, is something that we have moved away from when we talk about quantum mechanics, right? When we're talking about, let's say, the motion of the electron in an atom, right, there is a certain degree of, well, for lack of a better word, fuzziness, or you could say a lack of indeterminacy, or rather presence of indeterminacy, which happens, when we talk about the electrons themselves. So Heisenberg, when he was having this discussion of, he was thinking, in Heligoland, he went to Heligoland, he was thinking about how to explain the anomalies that exist with the spectral line aspect of things. He then came forward with this idea or thought that, instead of looking at it in terms of the Bohr atom, for instance, right, he would just focus on the observable kind of outcomes, right? What are we getting in terms of the experimental outcomes, in terms of the transitions, right? The radiation spectrum and the transition, so to say, and formulate his entire physics or the framework, the theoretical framework in terms of that, right? So now we know that as we move forward, the SPDF orbital kind of picture of things, where we have different kinds of ways in which the electron is oriented in different energy levels. We cannot quite talk about the trajectories anymore, right? There is no way in which there is a deterministic side of things. And that is very important to understand when we talk about quantum mechanics, of course, right? So when I say that it was not classically visualizable, right, that is what I primarily mean, which is that this very definite way in which the electron could be moving, or, you know, the various aspects, the dynamics of it can be explained, was not quite holding ground anymore, right? And it was more mathematical. It was very abstract in its own way as well, which gave rise to predictions or outcomes which coincided or aligned better than with many of the experimental results that came about before that and after as well. Yeah.
May I ask a question?
Yes.
Am I audible?
Yes, ma'am.
Yeah. See, actually, people all over are talking about quantum manifestations, entanglement, and things like that. That is a word these days. That's a buzzword now. And
Yes.
people have spent whole lifetime in understanding quantum mechanics, and we are still in the process of understanding. I don't think that we've understood it completely.
Yes.
But of late, people are using quantum manifestations in terms of explaining yoga, meditation, and they're talking it about, you know, quantum entanglement and then Snooki action of the Einsteins. I happened to attend one seminar. When they said quantum manifestation, I was so interested. After a certain period of time, people are talking what nonsense. So how do we stop this kind of things? And entanglement,
Yes.
we talk it in terms of physics. People are not talking physics. Other than physics,
Yes.
they're talking.
Yeah.
So
I'm so happy, ma'am, that you have brought this point up, right? And this is a very, very important point. I think there is one way in which this can be definitely summarily removed from the picture, and that is very simple. So there is this aspect of interconnectedness that people talk about, right? The spiritual aspect of interconnectedness, there's philosophy involved, and so on and so forth. But what we're talking about in quantum entanglement is not quite causal interconnectedness, is the first point, right? We're not talking about, for instance, if I were to change, I do a local operation in one side of my entangled channel, right? Whether that will have an impact on the entanglement structure itself or the other particle in the entangled pair is not going to be the case, right? There's no causality in that sense, right? There is a non-local correlation that exists, right? So there is a fundamental difference in the way we have to the conceptualization is done there, right? So there can be no comparison in that sense, right? There is no parallel per se, right? And so we have to be very careful, right? When we even talk about insights or resonances and, you know, metaphysical resonances, one has to be very careful about the application of these in the various places they are being applied, right? And the ways they are being applied, right? So I am extremely particular about this aspect because I find this a little problematic, right? When we are kind of conflating two very different ways of thinking into in a very trivializing way. I mean, it is not serving either of those subjects or fields, right? It is actually kind of, you know, taking away from both of them, I would say, in a way, right? So one has to be very careful about it.
Non-physics is what they're talking, and they're calling it by this name. So
Yes.
when we say entanglement, we really got entangled by these nomenclature.
Right.
Thank
Yes.
you. Thank you,
Thank
sir.
you. Thank you.
Ms. Bansil, you can go. Go ahead. Ask your question. Bansil.
Yes, thank you, sir. So, sir, if we see reversible evolution, so we picture reversible evolution through Schrodinger's equation, right? Which we represent through Hamiltonian operator. Am I right?
Yes.
And if we see an irreversible revolution, where we say that wave function collapse, which we represent by projection operator. So my question is there any accepted explanation for how to represent state collapse in Heisenberg picture?
So in the Heisenberg picture, because we're talking more about the operators themselves, right? I mean, so the evolution of the operator and the matrix mechanics, right? There's of course a one-to-one correspondence with eigensystems and so on and so forth. So you can definitely talk about it in terms of that, right? But if you're asking me more foundationally, what is the wave function collapse and how one can explain that?
Yeah.
Then I would rather go towards the entanglement side of things because I, come from that area of research. So decoherence theory is one aspect of things. We talk about how the classicality emerges from the system-environment interactions and correlations, right? And that leads to the collapse or the reduction of the state and the onset of classicality, so to say, right? So that is, again, one of the theories. I mean, there's a slight debate about some of the aspects of it. But in terms of the Heisenberg picture directly kind of explaining it, I would say that isn't it very natural? I mean, because the wave mechanics or the matrix mechanics, so to say, right, would lead to the eigensystem kind of decomposition and looking at the observables from there on, right?
Yeah, sir. Okay.
Yeah.
Thank you, sir.
If there are no questions,
may I ask one question?
yes, sir. Yes, sir. Deshmukh sir, please.
Yes.
Welcome,
thank
sir.
you.
Welcome to Professor P.C. Deshmukh, sir. Please.
Yeah, Mrittunjoy.
Yes, sir.
I really enjoyed your talk. It was very fascinating. You covered fantastic ground. I have one very small question about Jordan's contributions, because you visited the historical aspects so comprehensively. Is it true that Jordan was a major contributor to this whole idea behind the uncertainty principle? In fact, he was a contributor to many other things, including the second quantization methodology and so on.
Yeah.
But perhaps he did not get as much credit as Heisenberg and Bohr, probably because of his political positioning. Is that, did you come across any literature on this?
Yeah, I have no, I have not read all that much of Jordan's specific aspect on this front. But I do know that his contribution in the formulation, the mathematical formulation, was quite important. It was very fundamental in its own way. But because there are many gray areas in terms of annotating and, looking at the specific contributions essentially at times. Especially when you're talking about Max Born, somebody of the stature of Max Born and Heisenberg, so to say. So I wouldn't be in a very strong position to answer that beyond a point, because I'm not aware of the exact correspondences or the contributory aspects, if demarcated as such.
Yeah, sure. Yeah, I know it is a sensitive area, and not much literature seems to be available on that.
Yes.
But there seem to be some hints here and there about it. So thank you very much.
Thank you so much, sir.
Vinod Gupta ji. Okay. Priyamvada, please. Priyamvada, you can ask your question.
Yes, sir. Good evening, sir. I am Priyamvada. I'm an undergraduate student in physics.
Yes, please.
I want to ask a question about quantum entanglement.
Okay.
And I'm a person who's keenly interested more towards astrophysics, sir. So I want to know how quantum entanglement can perhaps help in discovering a few more mysteries in astrophysics, like perhaps solving singularity or like dark matter or dark energy. Is there any possible way that quantum entanglement would come into play?
That's a very fascinating question, because because quantum mechanics, of course, deals with, as you may know, the very minuscule, right? The subatomic particles, and we're talking about cosmological scales. So they actually come on the two ends of the spectrum, so to say, in a manner of speaking. However, having said that, there are specific areas of research which are looking at, for instance, information or quantum information or quantum emissions from, let's say, systems with high gravity kind of systems, so to say, like, even black holes for that matter. There's an aspect of information paradox one talks about with respect to emissions thereof. There is also this theory which is called, and you may be interested in looking at it, although I'm not sure whether you will have the tools to look into it beyond a point, which is called as ER is equal to EPR, right? Which is basically talking about how an entangled pair, an entangled kind of pair of quantum systems actually has an analog in terms of an Einstein-Rosen bridge, right? Which is basically, well, people talk about in terms of wormholes, right? Wormholes in cosmology and so on and so forth. But again, that's a fairly theoretical kind of area of research. There is not much in terms of being able to kind of prove it conclusively. But in terms of this aspect of ER equal to EPR, I always find that fascinating. What it is saying is that there is an analog of a wormhole, if you will, an ER Rosen bridge, Einstein-Rosen bridge, for every entangled pair of quantum systems, so to say, right? But other than that, I would say that they are on two sides of the spectrum. So the interfaces are quite limited, I would say, unless you're looking, of course, at quantum gravity and formulations thereon as well, where correlations between different fundamental units obviously matters, and that is also looked at in its own way, right? So that would be my response.
Thank you, sir. I will definitely look into the Einstein-Rosen bridge. Thank you, sir.
Thank you, sir. Thank you very much for answering all the queries posed by the participants.
Thank you.
On behalf of all the participants and as the organizing secretary of this program, my heartfelt gratitude to you for accepting this talk. And we are very much thankful and grateful to you for accepting this invitation and sharing your knowledge on quantum mechanics with all of us. There are many budding students are also there. They are very much inspired by your lecture. Thank you very much, sir.
Thank you for inviting me. Thank you for having me here. Thank you.
Thank you, sir. Now let's go to the second part and very anticipated part, that is interview with Professor Ajoy Ghatak, sir. Many of us spoke till now. As a graduate student and also as a teacher, we all have gone through the book Optics by Ajoy Ghatak and also Quantum Mechanics by Ajoy Ghatak, sir. It's my privilege to invite Professor Ahluwalia, sir, to interview with Ajoy Ghatak, sir. Before Professor Ahluwalia, sir, the National President of IAPT, interviews with Professor Ajoy Ghatak, sir, I request Dr. R. Komala ma'am, Secretary IAPT RC22, to read the profile of Professor Ajoy Ghatak. Komala ma'am, please.
Good evening, one and all. It's a privilege for me to introduce Ajoy Ghatak, sir. Ajoy Ghatak, sir, is currently Honorary Professor at Optics and Photonics Center, IIT Delhi. During Jan 21st to December 2022, he was the President of the National Academy of Sciences, the oldest science academy in India. He did his MSc from Delhi University and PhD from Cornell University. He is a fellow of Optica, formerly OSA and SPIE. He has authored several books, including his undergraduate text on optics, which has been translated to Chinese and Persian. He is recipient of several awards, including the 2003 OSA Esther Hoffman Bellar Award, the 2008 SPIE Educator Award, which was in recognition of his unparalleled global contributions to the field of fiber optics research and his tireless dedication to optics education worldwide, and also the CSR 1977 SS Bhatnagar Award. He received the OSA 2020 Sang Soo Lee Award for his seminal role in the development of fiber optics and guided wave photonics and for pioneering optics education in India, and the 2021 Sastra G.N. Ramchandran Award for Excellence in Physics. His book on quantum mechanics is now 50 years old and is the occasion of the day. We extend warm welcome to sir, and I hand over session to Madhusudan, sir.
So I think we can begin. If Dr. Madhusudan, may I begin?
Yes, sir, you can take the sessions.
Okay.
Yes, sir. Yes, sir, you can start.
Right. So thank you very much. I think it's a privilege to have this very special session today. and it will be a great opportunity for me to be with Professor Ajoy Ghatak today and talk to him uh, about what has been the most, I think, important contribution to the physics education in the country. I think Professor Ghatak has a very illustrious career, and you have already heard about it. I don't think that I should really repeat that. Everybody knows about it. Uh, the best part of this conversation, which I am looking forward to, is this: that we will come to know that the kind of experience his book has brought in learning of quantum mechanics has really inspired not just one generation of students, but a very large number of people in the country, students of physics, students of engineering, or students of other physical sciences also. So welcome, Professor Ghatak, for this conversation.
Thank you.
I'm happy that we are here celebrating International Year of Quantum Science and Technology. And I think holding of this series of lectures, which we have decided to continue for whole of the year, every month we will have this session, is because of your inspiration for inspiring us in a way. So let me begin. And I think this is from my side also a kind of I would like to have a peep into what went into your mind to really take up this kind of a project. And I would start with congratulations on the very enduring popularity of your book, Quantum Mechanics, whose first edition came in 1975. And I'm proud to say that that edition is with me. Maybe when I meet you personally, I will get it signed also from you.
Thank you.
So, and it is definitely very popular. And its second revised edition came after 2 years. So that means you were continually evolving with the project itself. And today it has evolved into a book with the title, not just Quantum Mechanics, but Quantum Mechanics, Theory and Applications, and with double the number of chapters. That is also interesting about this latest edition. Can you share with us your motivation for writing this book 50 years ago? And how did you and your co-author, Professor Loknathan, came together to work on this project?
Thank you. Thank you. Can you hear me?
Yes, sir.
Thank you very much for this, organizing this event. First of all, I must congratulate Professor Aluwalia for this year-long celebration and having every month 2 or 3 days of this meeting is really wonderful. And I would like to congratulate you and all your colleagues for this relentless effort in contributing towards quantum mechanics. Really, we are very grateful. Ever since you took over the presidency of IAPT, it has been so dynamic, so vibrant, and I'm really very happy about it. Secondly, I thought I would, when Mrittunjoy gave a very beautiful theory of quantum mechanics, very beautiful. I really enjoyed it. And so I would like to give a little bit of history of my getting into quantum mechanics. First of all, I did my BSc from Agra College, which was at that time a very good college, very nice college. And I wanted to do MSc there. But my father, who did his DSc from Allahabad University, insisted that I should go to Delhi University. And because he was a classmate of Professor Daulat Singh Kothari, most of you must have heard his name. So I did my There was no CUET or any kind of examination. That's what I keep telling. So I just applied, and there were 5 of us from the past course from Agra University who were there, Agra University, Rajasthan University. And we joined, and we had in the very first year teachers like Professor Majumdar, Professor Kothari, who taught us, and later a little bit Professor Olak also taught us quantum mechanics. And I would like to tell the younger generation who have Professor D.S. Kothari and Professor Majumdar were outstanding teachers, and we fell in love with quantum mechanics and the way he used to teach. Professor Kothari would teach us he prescribed Dirac's book, and Dirac had given a course of lectures at Tata Institute just before that. So there was a notes which was available for 3 rupees. 3 rupees. The Dirac's book was available for 24 rupees, and the notes were available for 3 rupees. And we got those notes, and he just followed Dirac's book. And Professor Majumdar would do from Schrodinger's, as Mrittunjoy pointed out, Schrodinger's development introduced the wave function, Schrodinger equation, and things like that. And both teachers, so my interest in quantum mechanics, first of all, generated from these 2 brilliant teachers. Then I was fortunate to get admission to Cornell University. And of course, I'd never worked with Professor Bethe, but my thesis advisor was Professor Bethe's student, but I worked in neutron transport theory. But Professor Hans Bethe gave 2 courses, one on basic quantum mechanics and the other on intermediate quantum mechanics. And those were beautiful lectures. Hans Bethe was a very meticulous speaker. He will prepare every talk. He will come on the dot. And it was a pleasure to listen to him. And the whole auditorium for the basic quantum mechanics course, the whole auditorium will be filled with senior professors and teachers. And he gave another beautiful lectures which I attended, which I was very fortunate to attend. Now, the difference between the quantum mechanics course that I learned in Delhi University and in Cornell was the fact that although both Professor Kothari and Professor Majumdar were outstanding teachers, but we in India did not solve problems. Our questions will be something like, right, something like derive uncertainty principle or write an essay on certainty principle and give the Stark effect in hydrogen. That would be one full question. That, right, derive the Stark effect in hydrogen atom, use perturbation theory and things like that. So there were very set number of questions which would be which we have to study, and we studied just a large number of questions and of course the concepts behind them. But we did not, even in classical mechanics, which was taught by Professor Aulak, we did not solve problems. Now, solving problems came in when we came to Cornell University, and then we solved a large number of problems we discussed with our friends and colleagues, and it was a great experience because I learned a lot. That is the thing. So then I worked in Brookhaven National Laboratory. When I came back and joined IIT Delhi in 1966, then Professor Lokanathan was there, and Professor Lokanathan was teaching quantum mechanics, applications in quantum mechanics. And Professor Lokanathan is about 10 years senior to me. He had done PhD from Columbia and worked with Serber. And I, although he was 10 years senior to me, he was an extremely friendly person, and we would talk, and I would always enjoy talking to him on quantum mechanics. And I even sat in his class. He was doing atomic and molecular spectroscopy applications in atomic and molecular spectroscopy in class. So I would attend his lectures, and our friendship grew. Although he was senior to me, but he's a remarkable person. He's right now in Bangalore. He's 95 or 96, and he still speaks with great clarity. And so that's how our friendship grew. And then within 2 years, what happened was he got a professorship at Jodhpur. And And he decided to leave. Professor Sodha was the head of the department, and he called me and he said that since Professor Loganathan is leaving, you take over the quantum mechanics course. And that's how I started teaching quantum mechanics. And then at IIT Delhi, we had the tradition, particularly among the undergraduate students, to give a large number of tutorial sheets. And that was not so popular in the master's program. But since I had the experience from Cornell University, so I started giving problems and sometimes the solutions and things like that, and discussing this. So then initially, and Loganathan also gave some problems and solutions and things like that. So we started building the course based on giving problems and working them out and asking some problems in the question papers also. And then within 2-3 years, we realized that it will be really worthwhile understanding quantum mechanics through problems. And I would go, Loganathan would also come to, Professor Loganathan would also come to Delhi, and I would also go to Jaipur. By then he had come to Jaipur. He took over. Within 1 year, he got shifted he took the professor position at Jaipur. Babulal Saraf was there, and Professor Saraf asked him to join Jaipur. So he came there. Jaipur was very close. So I used to go there just to meet him and talk to him. And then suddenly in one of the discussions, we thought that we should write a book on problems, in small book, just problems and solutions, problems and nothing else. In fact, the contract that we signed with Macmillan had the title Problems and Solutions in Quantum Mechanics. Then I think Professor Sodha probably advised that in beginning of all problems, you should give a concise summary of the theory. So we said that, all right, probably the first edition, which I still remember the price of the book, we got the NBT subsidy, and the price of the book was 16 rupees 50 paisa. And one of my students said that if you get a 10% discount, it is available for 15 rupees, 15. That was really incredible. That's how that also played a role in becoming, in the book becoming popular. It was incredibly cheap. But the main part of that thing was we collected, some of them we generated ourselves, some of them I learned from Professor Loganathan himself. And that's how I became, and he also, of course, he contributed a lot in the understanding and understand. So our main motivation was understanding quantum mechanics by solving problems. It is a little different from what Mrittunjoy has been telling. And basic quantum, even today, I find Heisenberg's paper, I try to read that, and I find it difficult. I really find it difficult. And this is what Weinberg, I saw the Weinberg quotation that Mrittunjoy mentioned. It was a beautiful quotation, and it is so true. And then came Feynman lectures, The volume 3 was a masterpiece, and the Stern-Gerlach experiment. And I loved teaching from Stern-Gerlach, the Stern-Gerlach experiment that Mrittunjoy mentioned. And so that's how we thought that we will tell the younger generation, try to tell the younger generation to understand the basic concepts in quantum mechanics through experiment, through problems, through understanding Stern-Gerlach experiment, and so on, and some things on scattering theory, which came later and things like that. But that was the main motivation. So we built up a large number of questions first, and then we worked out the solutions, and sometimes a little bit of numerical solutions and things like that. And that evolved because of the students. And another thing that I would like to mention, at IIT Delhi, we were very, very fortunate to have outstanding students. That is for sure, very good students. At least 60 to 70% of the students will be very motivated, and almost 100% attendance in the classes were small, 20, 25 students, but very, very motivated. So it was a challenge. You cannot say anything wrong. You have to First, understand it yourself. Make no mistakes. They will catch you if you make mistakes, and then they will work out the problems and interaction with them. So I was at that time quite young, and interacting with young students, very bright students. It was really a very enjoyable experience. And then what? Just one more last thing. And then what Professor Babulal Saraf did was he made me a member of the Board of Studies in Jaipur. I was a very young assistant professor, so I thought it was a big thing. So I would go for all Board of Studies meeting, and by then our friendship and this thing collaboration will grow, and that's how the book came out.
So I think it's just great. But there is another very striking thing which I find in your book is this. Problems are there. Definitely, there are lots of problems which have been solved. Normally, when people teach and go in the classroom, they will present Schrödinger as his Schrödinger equation only, and then they will start talking about it, but never, talking about Schrödinger or Heisenberg or Dirac or something of that kind. Your book starts with their Nobel lectures. I think, what was the motivation of bringing those lectures right at the beginning of your book itself?
We paid money. Actually, Macmillan paid half the money. They charged royalty for that. Got permission. I think very nominal. At that time, $100. So Macmillan said that, all right, we will pay the royalty. They were reluctant. So I think we ended up paying half the royalty ourselves and half the royalty then. So they shared. And so we felt that the Nobel lectures, and by the way, in the later editions, we removed it because now the Nobel lectures are freely available on the internet. Freely available. You just write Nobel lecture of Heisenberg or Nobel lecture of C.V. Raman and the whole document comes in. But at that time, we felt that the Nobel lecture, when one prepares, it is to the general audience. So bringing out, making the average person understand the basic concepts of the research work that has led to the Nobel Prize is beautifully manifested only in the Nobel lectures, which has very little equation, only concepts and things like that. So we both talked about it, and we said that if the student learns how Heisenberg, Schrödinger and Dirac presented their theories to the general audience without using mathematics, and in 10, 12 pages, that will be a very good contribution. So that was our motivation. And now, of course, this is a very big thing that has come up with the internet, that now Nobel lectures are freely available and things like that. So that's how we...
Then later you brought in Vesukov's wonderful article in your book also.
Yes, the Weisskopf article. That for that also we paid a small amount of money, and I wrote to the press that can be used at. They charged very nominal, $75, and this was long time back. Weisskopf article, so $75. So we paid that, and then I wrote to Weisskopf also. I still have that letter, and he immediately signed. Weisskopf wrote a very nice thing. I'm so glad you are using this. You have my full consent. He wrote it and he signed it. So that's a very beautiful article. Very beautiful. I love reading that. So I thought that let people read. As has been mentioned in some of the questions, basic concepts in quantum mechanics. And you see, and then came Feynman lectures. In the Feynman lectures, the electrons pass through both the holes at once, and the collapse of the wave function, which Mrittunjoy also discussed, the collapse of the wave function, etc. So those things we tried to put in the later editions and things like that.
So we can see, sir, without internet, writing a book must have been like a startup of that era, in fact, and a lot of intellectual engagement is also involved, and you traveled to Jaipur, and maybe Professor Loknathan sir also must have been doing vice
No,
versa.
most of the time, because I was younger, so most of the time I went to Jaipur, and of course I was a member of that board. So twice, thrice a year, the board meeting will be there, and I would take the train or the bus and go there, and sometimes stay with Loknathan. Sometimes he had a wonderful. His wife has passed away recently, and very hospitable, very warm, and very affectionate, and so.
But it is also interesting to note that Professor Babulal Saraf saw that spark in you and made you. Professor Babulal Saraf also saw a spark in you, and he made you, come to Jaipur as often as possible.
Yes. Babulal Saraf played a very, very important. He was also very interesting. He would show me his experiments, and it was. Physics, Professor Babulal Saraf would do all the experiments and show that. And then we got the entire kit at IIT Delhi, and he was so happy. And I had great admiration for Professor Babulal Saraf and Professor Loknathan. I had tremendous admiration. I will tell you something. Babulal Saraf, I knew him because from Agra. He taught at Agra College also, but by the time he started teaching, I had already left Agra College, and he was the head of the department there at one point of time. So he knew me from Agra College, and the apparatus, the experiments that he generated at Jaipur, the creation, that was very good. And probably he saw that I was really motivated, and I would always talk physics and things like that. So he said that, Ajay, you should become. Yeah, I was like a student, He was much older than me. He says, Ajay, you should be our board of studies member and tell us how to improve our syllabi. That was the greatness in it. That is the thing that I'm myself inspired to see. I'm grateful to you that you asked Mrittunjoy. He looks so young, so dynamic, and we should learn from the younger generation. I want to learn entanglement from Mrittunjoy, things like that.
Another very interesting aspect from which I would like you to tell us. If we look at quantum mechanics as a field, it's a very vast field now. And as I mentioned, now your book has double the chapters than when it started. So can you tell us the evolution of your book also to the present format, which is there? And I think maybe you must have been thinking about or balancing about the quantum revolution too, which is actually right at our doors, knocking very hard. Our students should do that, and all those things. Please tell us that also.
Yeah. You see, what happened was, once I started teaching quantum mechanics, then somehow I've been teaching quantum. I must have I stayed in IIT Delhi for about 40 years. 40 years, yes. And 2-3 years I was away outside on sabbatical, twice on sabbatical and things like that. So let us suppose, but I must have taught that course on either quantum mechanics 1, there were 2 courses in quantum mechanics 1 or quantum mechanics 2, and also many times optics. I would teach that course. So my head of the department, whether it was Professor Sodha or anyone, they will always advise me that you take one of the quantum mechanics course. So I ended up teaching quantum mechanics course. And so every time I would prepare my notes, that is how so many editions have come out. And as I mentioned before also, that there were several projects also I did, master's projects I guided, simple calculations and things like that. And and which motivated me to present the same thing in a different way, And lately, when the concept of entanglement came in, I have now in the latest edition a small portion on quantum entanglement. That I take the example of the calcium atom liberating 2 photons which are entangled, and you measure the correlation of the two, and the derivation of Bell's inequality is not novel. I must initially mentioned. It is not novel, but it is little unique, and I have tried to explain that very simply. Then I tried it out in the class, and people understood the Bell's derivation and Bell's inequality, and that Bell's inequality and quantum mechanics are either one is true or the other. Bell's inequality depends on hidden variables and very simple analysis. So things like that. So that has given me a lot of fun. I have spent a lot of time in understanding and trying to explain complicated things in a very simple way. And one thing that I keep talking to my students is that the uncertainty principle is contained in the solution of the Schrodinger equation. And then I quote Feynman, and so I say that electron is neither the main thing that I always try to tell them is neither a wave nor a particle. Then the question is, what is it? It is described by, let us suppose, the wave function psi, which is the solution of the Schrodinger equation, and the Schrodinger equation cannot be derived. They don't believe it because some of the universities have still a question like derive Schrodinger equation. They say that. Then I say that I'm not saying myself. I am quoting Richard Feynman, who said that Schrodinger equation cannot be derived. Where did it come from? It came from the mind of Schrodinger. So these things, amuse me. Even at this age, I get amused when I read. I get so enthralled by this descriptive form that people like Richard Feynman have given in that beautiful book. And I listen to that lecture, and I tell my students that now lately I do workshops here and there in Delhi, and I tell them that, you see, I studied at Cornell University. I left in '63, and then I was a postdoctoral fellow at Brookhaven, came back in '64. And one of my greatest regrets was, and this is for all the young teachers and the young students who are today present, I would like to mention that my greatest regret was that I could not hear Feynman. Feynman came and gave those beautiful 6 messenger lectures at Cornell, and it was my greatest regret. But now you can hear them on internet, and you can hear them free of cost as many times as you like. And this is a great thing that has happened. So people of this generation are more fortunate,
very lucky.
And the transcript of the lectures are there, and it is so beautiful. And the internet revolution has helped so many, and because of that, today we have this meeting. You are sitting probably in Shimla. I'm in Delhi somewhere, and Madhusudan is in Telangana and things like that. And this is something remarkable that has happened. And I talk to my son almost every day, who is in California. this revolution, and so therefore the students have so much access to education, to knowledge. If he does not have a good teacher in quantum mechanics, then he has Feynman lectures to fall back on, or something else. And there are so many other lectures given at the MIT and things like that. So really, right now the opportunities are endless.
But there is another thing which I would like to ask you in this context is this: that, as a teacher, when we start our teaching, and normally in higher education, we don't get any kind of a training to teach, B.Ed or M.Ed, we don't have that. But we have a role model as a teacher, and you have really mentioned very many names. Would you like to tell us who was your role model and how that role model must have influenced in writing your book also?
No, my role model as a teacher has always been Professor Daulat Singh Kothari. I have never seen such a person, man of tremendous simplicity, and so he was my role model. Then when I came back from USA, I was a pool officer. I don't know whether most of the younger generation will know. This is for unemployed scientists. So I was homesick. I came back after 2 years at Brookhaven National Lab. And there's one thing that I want to mention, that when I came back, the director of our unit, not the director of the lab, director of our unit, came to my room And he said, Ajoy, why are you going back? Now, today, when a young assistant professor is trying to go to somewhere else, will the vice chancellor go in India and say that, why are you going? You see, so I was very fortunate to get a outstanding thesis advisor, outstanding teachers but in India still there is a lot of hierarchy. I must say, a lot of hierarchy is there, and it still is there, unfortunately. And we have to remove that. But that hierarchy was not there. But when I came back, so I was a pool officer, and my research work overlapped with that of Lakshman Singh Kothari, who was son of Professor D.S. Kothari. So Lakshman Singh Kothari, Professor, he's much senior to me. He was also an extraordinarily good human being. Oh, and we worked in neutron transport theory at that time. And so I would go to his home, and he was in the house of Professor, occupied by Professor D.S. Kothari, and sometimes Professor D.S. Kothari would just sit there with all four of us and just keep on telling some stories or something like that and motivate us. But the simplicity of that man and the dedication. And sometimes when I would teach later also. So my friendship with Professor Lakshman Singh Kothari was very close. And through him, I developed a very close relationship with Professor D.S. Kothari, so he was in all sense my role model. He was a Gandhian. He did not take salaries and things like that. I would always take. So there is a difference, but he never owned a car. He never owned a house. So he was, but this is what I tell today, that we had role models like Professor Majumdar, Professor Kothari, and other people who were really scrupulously honest, dedicated to teaching and research. Although there was a lot of difference, we will be scared to talk to them, but they will always talk with a lot of affection and these things. So, and the third thing that I would like to say is this, that when I started teaching, one thing that I did, I would give my life to it. You see, I will prepare, even today when I prepare my lectures, even if I have given that, so I will prepare. So I did the hard work, and that hard work gave me a lot of pleasure, and my students, I also have developed over the years a tremendous love for my students and colleagues and younger generation. And so it has been a very good life, and so I have enjoyed everything. I have enjoyed teaching. I have enjoyed experimenting with in optics. So I used to take the undergraduate lab in spectrometer, and I say that here is the mercury light, and it goes through it falls on a grating, and these colored lights come out. It is a gift of God. I see God in that experiment when I do the diffraction grating experiment. So I really loved those experiments, loved explaining to them that how is this diffraction happening and why is it happening, how is it splitting to these colors. So both with optics and quantum mechanics, there is a lot of interplay, because it is the question of what is light that eventually led to the evolution of quantum theory and wave-particle duality. And who discovered wave-particle duality? I say that Einstein in 1905, when he gave that 1905 photoelectric effect paper, or the concept of the light quantum, things like that. So I really enjoyed, and my students were also very good. So that's how it has been a very fulfilling life. So I have enjoyed the profession. So it reminds me of a person who said that I saw the TV interview, that she was a lady who was singing in the church, and she said that I would do it in any case. I sing for God, and I get paid for it. So I enjoyed. I would have done that even free, but I got paid for it.
There is one more aspect to your book. that there were some immediate students who were available to you, whom you were teaching directly.
Yes.
But there have been a lot more students available to you who were not directly with you, but they were like, Eklavyas and trying to study from your book. Have you encountered, such students also who came to you and they mentioned about your book or specific, aspect of your book, and how you got, those kinds of feelings from them and how you reacted to those things?
I will give you one example. I don't know whether he is here or not. There are many examples like that. You see, I have retired from IIT Delhi a long time. It has been over 20 years, but I still try to keep active. And one of the persons with whom, of course, I still have colleagues at IIT Delhi, Anurag Sharma, Varun Kumar, and other people who still keep coming to me. But then I have another person who probably had read my book or something like that, who just came to me. He did PhD in Bardhaman University, Anirban Pathak, and he came to me. So maybe my books brought him to me, and he is an expert in quantum optics, and he teaches me, and we began a collaboration. We wrote a few books, small edited books, and so so that is the advantage. People know me, fortunately, God's grace. And for example, even Dr. Madhusudan said that he had probably read my book. So that has given that people who live in near Delhi, they have read my book. They come to me sometimes to say, just to meet me, and then we enjoy our discussions, and then we start working together. So that is something which is God's gift. I mean, I'm so fortunate in that sense. So, and one such example is Anirban. I have actually authored 2-3 edited books with him, and in which each one of us has chapters there. And then we are organizing a small workshop next month and things like that. So these collaborations develop. Then I have also students in several colleges in Delhi University. And so I go there. So I keep myself busy. That is good for me, good for the students and things like that.
There is one thing which I would like to tell. Professor Arvind Pathak is also here, right in the audience.
He's here. I didn't say.
He's very much here. It is nice that you mentioned about him. Another thing which I would like to really mention this is that now the subject of quantum mechanics itself, it's gone so vast that now we are talking of quantum mechanics, particularly by compartmentalizing. For example, if we want to work in quantum computing or if we want to work in quantum information science, people are talking about, don't worry about the fundamentals, come to the kind of mathematics which goes into it. And an engineer can become very adept in utilizing all those things. Mrittunjoy also here, I think I would like you to really reflect on that. Is it really going too big and we are losing the joy of learning quantum mechanics as part of that?
You are asking me?
Yes, sir.
Yeah. No. But as you very correctly mentioned, that quantum computing has come up, this thing. And only, I mean, you will not believe this, only day before yesterday, I was asking Anirban that I understand the qubit, but how do you make that qubit propagate through empty space or something like that? That is still, so I asked him that when I meet you next, you have to tell me, you have to explain to me. And so things like that. So for that, you have to know some aspect of quantum mechanics, but you did not, for understanding those things, you need not understand, you did not go through deep into scattering theory or WKB approximation and things like that. So the time is limited. And in fact, I told Anirban once that we have to now formulate our quantum mechanics course to take care and suggest to different universities to take care of the new things that are coming, which requires quantum mechanics, but we did not go through other details. quantum mechanics to understand quantum computing, quantum mechanics to understand nanotechnology, and things like that. So, of course, quantum mechanics itself is so vast, as we heard from the first speaker, Mrittunjoy, that if you go through, you can spend years just to understand how Heisenberg wrote those three papers right in the first year. But then you spend your lifetime on that, then how will you do quantum computing? So what I feel is that syllabi have to change, have to evolve with time. And so therefore the new applications that are coming in, the time is limited. If you, let us suppose a person enters the BSc honors or MSc level from at say 21 or 22, and he has 2-3 years. So he has to understand work later in quantum computing. So quantum mechanics has to be divided, and then only that portion which is relevant there, and little more and basic concepts, etc. But other things you may skip, or may give you an additional reading or something like that, because if you are giving a MSc in physics, other subjects have to also come in. So evolution of the curriculum has to be there. But if there is a book on quantum mechanics, it has to have all aspects of quantum mechanics, that is for sure. But our courses have to change to take care of the modern things that are coming up. Similarly, in experimental physics, right now semiconductor technology has become so important, and so experiments have to go in that direction also. So we have to evolve.
There is one question which I cannot stop myself from asking you, is this. There is always a talk that when we look at physics curriculum in schools, we have never gone beyond Bohr's model there. Is there time now it has come that the school curriculum, as far as teaching of what so-called modern physics is concerned, something regarding these new ideas of qubits, etc., should be taught to them at that particular stage itself, so that they may get interested into something which is becoming the real fun these days in research as well as in technology?
I hope we can do that. I hope we can do that, but I do not know how I will be able to do. I can teach them little bit of quantum theory, a little bit of wave particle duality, but I cannot go to the solution of the Schrodinger equation. I cannot. It will be too difficult for the first. So, but the concept of measurement, collapse of the wave function, probably can be taught. And that when you have the beam splitter experiment, a single photon source, the photon is here and there. If it can be injected to the mind of the class 12 student, that when you have a single photon experiment or a single electron experiment, and then there are two paths. It is here as well as here, and then it can be superposed. It can interfere with itself to produce the interference pattern. I think these concepts have to come in now. A student in class 12 will be able to, should be able to, can be made to understand this. So this part, I'm planning to sort of write some article and probably publish it somewhere, and maybe as a thin pamphlet or some PDF, and put it somewhere, that what aspect of quantum mechanics, quantum theory, that telling that the particle, that the electron or the proton or the neutron or the photon is neither a particle nor a wave. So फिर वो क्या है? What is that? And the answer is, I don't know. It is described by a wave function, but it is here as well as here. How is it here and how is it there? So this is a conceptual problem, and which has to be put into the mind of the young man or young girl right at the school level, so that that thing has to come in without giving any wrong information. That is the most important thing. Without giving any wrong information, and
there is one more aspect also, which is this, that the mathematics which we require for doing these, play with the qubits, etc., is basically Heisenberg's matrix mechanics itself. And manipulating that is also not very difficult to, manage in class 12.
No.
And it's very easy. And the most inherent property of non-commutation is also inherent in matrix mechanics itself.
Yes.
So maybe there is a lot of talk about all this in our IAPT also. We are conducting lots of small. You must have been watching us doing all those things. Finally, sir.
No, the matrices can be taught at the high school.
Yes.
I personally feel matrices can be taught, and solving a set of, say, 2x2 equations using matrices and things like that. That can be. Yes. Sorry, I interrupted.
No. Then there is one more thing which I would like to ask you is: are you really? I have been receiving. I'm thankful that you sent me your book also lately on here in Albert Einstein.
Yeah.
Are you planning to write some more books also? Are there some projects which are ongoing at the moment?
So there are some projects in my mind, but I'm also now 85. So my wife says that, why are you working so hard? I said that this is giving me fun. But since you mentioned that book, so I thought that I will tell you that the unique feature of that book was prompted me to write the derivation of E is equal to mc square, and is really very simple. And E is equal to mc square is taught both at the +2 level and also at the first year level. And the derivation that I have, actually, it is not mine. It is I collaborated with and that is also possible through internet. That with a senior professor in New York, Professor Beth Parks, and that you see, it is something like this: that I have a pi meson at rest. I can always do the Ghatak thought experiment of a pi meson at rest here, inside a train. I'm inside a train, and the pi meson is at rest, and it emits 2 photons of the same frequency. And so that is matter conversion to energy. Now, so the energy of the particle is therefore 2h nu naught. The pi meson disintegrates to 2 photons of the same frequency moving in opposite direction. Now I am inside the train, so therefore you are on the platform. So if you want to measure the frequency of this here and this person are different. The person for whom the source, the pi meson, is moving towards him, will see a Doppler shifted higher frequency, and the person from whom the source is, the pi meson, is going in there. So the 2 frequencies are different. So the energy that you will see on the platform is slightly more. And it comes out so beautifully. And the difference of the two is the kinetic energy of the pi meson. And you take the limit, in the limit of the velocity going to 0, it should be half mu square, half rest mass multiplied by the square of the velocity. And if you equate that, you get the equation E is equal to mc square. And that's such a beautiful proof. I'm very excited about it. And I'm really very excited about it. And I want at least this proof to be known. And this has been reviewed by 3 professors. I don't know their names. Reviewed by 3 professors, because we submitted it to American Journal of Physics. And all 3 professors spoke reasonably good about this is that it is using concepts which are known. Doppler shift we know, and conservation of energy and momentum. We also know that the energy of the photon is h nu and the momentum of the photon is h nu by c, and c is invariant. These are the things, these are the 4-5 factors that we know, and from that it beautifully comes out E is equal to mc square. So I am trying my best to sort of see that that it comes to right. I mean, for those who are attending this seminar, if you write to me at Ajoy, Ghatak@gmail.com, I'll send you the paper at least. Ajoy. It's a Bengali Ajoy. It is not Ajay. Ajoyk Ghatak@gmail.com. Then I will send you the paper. I'm really very excited about it. That's why I wrote to you.
Thank you for sharing your insights and experiences with us today. And finally, I would like to, ask to do us a favor. And that favor is very simple. We at IAPT is a very vibrant community in the country. We have a very interesting vertical from schools, colleges, and universities. And what kind of message would you like to give us so that the quality of physics education also improves in the country, particularly with the coming of this national education policy? There is a lot of stress about which you mentioned right in the beginning of the interview, that problem solving is the key to everything. If we really focus on that, maybe we can do a lot of good to the quality of education and the physics education itself. So what are your parting thoughts for this interview?
My parting thoughts, I'll put it in two parts. First of all, I would like to share my tremendous concern about one thing, and that is that in my generation, I don't know about your generation, Professor Aluwalia, but we never sat in a competitive examination. You see, when I did my class 10th UP board matriculation, I went to Agra College. And when I went from Agra College to Delhi University, there was no competitive examination. Now, I don't know what role IAPT can play, but we have too many competitive examinations. We have JEE, NEET, CUET. Imagine I'm a student or I'm parent of a student in class 11 or 10 or 9, and my son wants to do physics or chemistry or engineering. He does not know, he or she does not know. He has to do, he knows that if I do not go for the coaching class, I will not be able to get into IIT or a good institute. So now, most of the young students, bright students, are going for coaching classes. Now, I don't blame the coaching classes. Coaching classes are doing what we are making them do. See, many people criticize coaching classes. They say that coaching classes should be banned. Now, I do not agree to that one. Coaching classes are created by people like me, because we have developed the JEE examination. I was part of IIT. And because of that, we have coaching classes. And believe me, coaching classes teach a lot of problem solving.
Yes.
Teach a lot of good problem solving. They are very good teachers there. They are very good teachers there. And they teach, why today IIT students do so well going abroad? Because they do the problem solving part in those coaching classes, not in the schools. But they also miss the school environment. They also miss the school debates, arguments, and games and everything. So right now, in my opinion, that is the biggest problem that is facing. What is the solution? Solution is having a much larger number of institutes, good institutes run by the government. You cannot postpone everything to the private sector. So that is right now, my main concern is this. And the second thing is how to get good teachers. That is my main thing. If, not just in physics, but in mathematics, but in science. Good teachers, they are there. There is no doubt that there are very bright young men and women who are coming to physics or chemistry or something like that. But as you asked me earlier, Professor D.S. Kothari was our role model. We wanted to become D.S. Kothari. Are we, and really, we wanted to become, our ambition was to become one like D.S. Kothari or R.C. Majumdar or something like that. Are we projecting that kind of image to our younger generation? That is one question. So that how do we get motivated teachers, motivated students? But the students are also poor students. They are very confused. They are very confused. They do not know that 10th class whether to attend school or whether to attend college, whether to attend coaching centers. They do not know. So that is the main problem. But and IAPT has played a very important role in doing experiments, and people like Babulal Saraf and many others, so many workshops that each regional center is organizing. So things are going on, but today people are not coming to engineering or basic physics and things like that. Many people say that physics mein jobs kahan hai? Where are the jobs in physics? I say that there are jobs available. The country needs large number of education institutions. Today, in our country, a department will have 30, 40 physics faculty. I went to China, they have 250 faculty in one department. And the population is now, we are more densely populated than China. So you see, much greater emphasis on it. There are two things that government has to take. If you can play a small or a big role in that, convince Professor Sood or something like that, yes. Two things, health and education has to be with the government. Has to be with the government. He have to spend, of course, he will say that the government will say we have to spend more on defense. That is true, that they have to decide. But you cannot delegate that to the private sector. You cannot, one cannot. So these are random thoughts. You have greater experience with IAPT and motivating the teachers, motivating the students and things like that. And teachers becoming role models.
So thank you very much. The purpose of having this interview has been to get an induction effect of your inspiration to our community itself. And I think you really gave us a wonderful insight between how you evolved as a teacher, how you evolved as a researcher.
And I will conclude by saying, you see, today money has become very important, which is good. Everyone requires money. I also require money. So I tell the very young, if there are young students here or something like that, and they will say that physics mein paisa kahan hai? I tell them I'm 85, and today if I want to earn money, I can earn money through teaching. So there is money also in physics, in doing just physics teaching. So there is no doubt about that. On that positive note, yes. Sorry.
Thank you very
it has
much.
been really an honor for me to interact with you.
Thank you. We are grateful to you, and I express my deep gratitude to you for sparing so much time for us. Maybe a few questions from audience may also come, sir.
And then the audience is slowly leaving. It is dinner time for them.
Still, sir, we have a very good number. In fact, that shows we have a dedicated audience available today. Mr. Madhusudan, please take over further. Already one hand has been raised.
Yes, sir. Ritika, you can ask your question.
Yes, sir. Sir, I have two questions. First is, what are the key areas that are required to study quantum computing? If one has zero knowledge about it, this is one question. And second question is about, sir, that rotational levels and vibrational level. We often say that there are vibrational levels, rotational level associated with a molecule when it is vibrating and it is rotating. Yeah. But sir, being a learner, it's very difficult to imagine how this rotational level arises, how this vibrational level arises, how transitions between them is going on. It's good to have selection rule, but sir, it's very difficult to believe that is it really happening or not. So, sir, how to understand this or how to experience this?
If you have the latest, not latest, I think the sixth or the fifth edition, I did work out the rotational vibrational spectra of diatomic molecules. I have done that in detail, and only of diatomic molecules, and that comes out beautifully from the solution of the Schrodinger equation. And the first question, I would really like IAPT to come forward, and that's a very good point. And I had also partially mentioned that how to introduce quantum computing in the syllabus of our undergraduate examination, undergraduate. Now BSc honors, if you look up the Delhi University syllabus, it almost covers whatever we covered, you used to cover in MSc previous and things like that. So the syllabus has expanded in the BSc honors program. So introducing quantum computing by an expert who has taught quantum computing to undergraduate students. And one person, as I mentioned, Anirban Pathak, and many others, like Mrittunjoy, Guha, and Majumdar. And so many others can participate in that and frame a syllabus. That would be very good contribution of IAPT. Thank you.
Manish. Mr. Manish.
Yes, sir. Thank you, sir, for giving me an opportunity. Good evening, sir. Sir, I have a question.
Yes.
In the course of this talk, once you mentioned quantum mechanics and immediately you corrected yourself by saying quantum theory, not quantum mechanics. So I have a question. What is the difference between quantum theory and mechanics? What I told you that quantum mechanics must be a subset of quantum theory. So
Yeah,
in what manner it is a subset? What is the relation between them?
No, you are right. Quantum mechanics, as you correctly said, that is part of quantum theory. But what I meant is, the quantum mechanics means you solve the Schrodinger equations or something like that, Schrodinger type of equation to get the oscillator energy levels and things like that. That is too difficult at the school level. That is difficult. Solving Schrodinger-like equation is difficult. But understanding the basic concepts of quantum mechanics through simple optics experiments, or even electron, that it is that the path that the photon comes in, and it is in both the paths. And this concept, if it can be impregnated into the mind of a young student right at the class 11th level, then I think it will be good, because that it is in this path and this path. The concept of polarization can be introduced so that this can be S polarized, this can be P polarized, and they can be superposed to form a 45-degree polarized beam. This is very beautifully explained in a book by Anton Zeilinger, Dance of the Photons. So a book like that, Dance of the Photons by Anton Zeilinger, which does not solve any Schrodinger equation, but solve the superposition kind of experiments and things without going into equation. That is what I meant by quantum theory. And that those concepts, if that can be introduced at the school level. I would again repeat the book, Dance of the Photons by Anton Zeilinger. Zeilinger shared the Nobel Prize, 2022 Nobel Prize in Physics. So a book like that can be taken as a role model, as some guideline for outlining the things that can be taught at it.
Okay. Thank you, sir. Thank you so much.
Now it is the turn of Priyamvada.
Good evening, sir. I am an undergraduate student in physics, sir, and what I wanted to ask was about that I myself observed this, where the strength in physics students has been coming down every year. And I myself am very much interested, and I am fortunate to say that I wasn't forced into the field, but I've seen many of my classmates discussing how they really weren't interested but had to do it due to some external pressures or external opinions. So what do you think, or how could we change this, and why is it happening in the first place?
It all depends on the job opportunities. You see, you are going now. There is a craze for. I mean, I have seen engineering colleges, private engineering colleges, and I will not name them, but most of you know that most of them are doing. There are 2,000 admissions, 1,900 students are going for, 1,950 students are going for computer science because there are jobs and opportunities there. Unfortunately, you are absolutely right that people are not coming to physics because they think that there are not many jobs that are available. And that is partially true. That is partially true. But if you do quantum computing or something like that, and if you are good in it, so therefore, once you decide to enter physics, then you have to put your heart into it and take that risk, and I'm sure things will work out for you. And so my answer to your question is, there are certainly, it was, I must be very frank, in my times, getting a job as a lecturer in physics or assistant professor in physics was much easier than what it is now. That is the unfortunate part. So getting a job has become more difficult, and therefore people feel scared to take up physics. Having said that, but if you do physics very carefully and work a lot, if you are very passionate about it, I'm sure you have a good future. This is what I feel.
Thank you, sir.
It is little. I'm also concerned about your concern. I'm really concerned about your concern that
Yes.
when a young person, very bright young person, comes to me and he or she says that, sir, I want to do physics, but are there jobs in it? I don't know the answer. I really do not know the. Maybe Professor Aluwalia can give his opinion.
I fully agree with you, sir, that we need to orient our undergraduate courses so that the kind of opportunities which are coming because of the quantum revolution itself, because 6,000 crores are there in this quantum mission.
8,000.
They require people to handle all those things. And I think you are very right. If we really modulate our undergraduate syllabi and tune that to that effect, I think job opportunities will come. Physics
Yes.
are very good at doing anything, sir, because they have basically fundamental skills, problem-solving skills, etc.
Yes.
So I think we should not be very much, disheartened. We should keep on trying, bring new things into it. And maybe IAPT is raising a lot of hue and cry around this also, sir.
That's all.
So thank you. The last question.
Bansil.
Yeah, I'm so sorry, sir, if I'm making some noise from my background, because if I don't ask you a question, I'll probably regret. So, so my question is, as being an interest in core fundamental physics, I want to ask you that if I want to pursue theoretical physics, on what fundamental aspect one should focus on, rather it be an astrophysics, cosmology, quantum, nuclear, anything. If I want to pursue, or if I want to become a theoretical physicist, and what fundamental aspect one should focus
on? That is, there are so many. I think this question, there are so many fundamental theoretical physics that is going on right now, and I hear that India is going to get a LIGO in Pune in few years' time. This is gravitational wave detection and things like that. So if and when that comes up, there will be requirement of not only very good dedicated theoretical physics in astrophysics, cosmology, and all these areas, but also in optics, because essentially it is an interferometer and sophisticated calculations there and observations, both theory and experiment. So So even today there are institutes like Harishchandra Research Institute and the Center for Theoretical Sciences in Bangalore, Tata Institute, many other research institutes which are coming up, completely devoted to theoretical physics, and they are coming up. More will come up. You have Institute of Math Science in Chennai, and so therefore you have to first study very hard, study all aspects of physics. A lot, not you cannot study all aspects of physics. Learn for example, in the first talk today, there's so much of quantum mechanics to learn, and then you do astrophysics. Which one will have greater opportunities? It is very difficult to say. It is very difficult to say. All subjects are equally. Even quantum optics is a very important subject. Quantum basic quantum mechanics has also become very important. And then people are still doing string theory and other frontline areas. Those are also, there will be demand and things like that. The job opportunities, that is something that the future will tell. Hopefully there will be some, but there are much less job opportunities in these fields in America, for example. That is for sure. That is for sure. People are coming back to India in large numbers, and because they get a postdoctoral position very easily, but they do not get a regular tenured faculty position easily. So the job opportunities are becoming less. Nevertheless, if you are extremely good in it, then opportunities will be there. That is my feel. It is very difficult to give a very clear-cut answer to that question.
Thank you, sir. Last question is from Anushri. Anushri, please.
Yes, sir.
Yes.
Is it a good idea to pursue quantum computing for a master's degree, or is it a good if we pursue it as a PhD degree?
Both. I think it will be wonderful because quantum computing is coming in a very, very big way. That is for sure. And there will be now people required in universities and colleges where people of that expertise will be extremely necessary. That I'm absolutely clear about. So if you get an opportunity to do a master's in quantum computing with a specialization in that area, I think you go for it, put your heart into it, and you will do very well. There is no doubt in my mind. At least in this answer, I'm absolutely clear. In the previous answer, I was a little vague because I did not know. I would not know which one will you excel. But quantum computing, if you know the basics, if you know how to understand and apply, and that will require knowledge of quantum physics also, quantum theory also, quantum mechanics also, then you go for it and work very hard. But once you work in that area, you also can change your line of thinking, change your area of research slightly from here and there, and that is possible. That will be possible. But once your basics are clear, then you can work in slightly related areas also. But if you get an opportunity to work either for your master's or for your PhD in quantum computing, go for it. That's my advice.
Yes, sir. Thank you, sir.
Thank you, sir. We feel very much privileged to hear you. And the most important words I can learn from you: improve by doing each and everything, by putting our hearts into whatever what you call area we work on. So thank you very much, sir.
Thank you.
Professor Aluwala, sir, can I conclude?
Yeah, please go ahead.
Sir.
It has been my great pleasure.
Thank you very much, sir. I also thank all the participants for your time. Your you were there for almost 2.5 hours in this session. I request all of you to be present tomorrow also. Tomorrow we have 2 important sessions. We can listen to Professor Pratul Desai, and we can also hear to Professor P.C. Deshmukh sir on his book. With these few words, I'm signing off and thanking both the speakers, Professor Majumdar and everyone's hero, Professor Ajoy Ghatak sir. Thank you very much, sir. Thank you all for your active participation. I also thank Professor Alwale sir for guiding us. Thank you, sir. Thank you all. Let us wind the session.